What makes piecewise functions unique from other functions? As far as like using shortcuts to find the derivative. Why can't we just take a piecewise function and find the derivative of each piece and call it good? Anybody know? Okay, yeah, sometimes they're continuous but don't have a derivative because piecewise functions are exactly why we have corners and cusps. Piecewise functions are typically where those come from, right? Because this is an absolute value function, which is a piecewise, right? A cusp is from a radical, but we know that this specifically is the idea of like what piecewise functions do, right? A lot of the functions that we learned about in Math 3 with like cubics and parabolas and log functions and exponential functions, all of those are like smooth curves, right? Polynomials are smooth curves. A lot of the functions we deal with are smooth curves. So for the most part, when we learned about our shortcuts, if we could take the derivative of it, it would be a smooth curve, unless like it wasn't continuous there. It had vertical asymptote, so it wasn't continuous. The one thing that throws a wrench into all of those plans are the piecewise functions, because if you take a smooth curve and you take another smooth curve and you have them come together at a point, you don't know if what's coming together is smooth or not. Does that make sense? Okay, so when we deal with a piecewise function, we have to make sure that the function itself is continuous, that it actually, those two pieces touch each other. But we also have to make sure that when it's continuous, that the left-hand slope and the right-hand slope are approaching the same number. And we do that by making sure that the derivative is continuous. Because if the left-hand slope and the right-hand slope touch each other, if the derivative is continuous, those are synonymous. If the left-hand slope and the right-hand slope touch each other, the derivative is continuous, that's the same thing. Then that means that the slope is approaching the same thing, and that means that it's a smooth transition from one piece to the next, which means that that slope would actually exist at that single point, okay? So that's why piecewise functions have a two-part process instead of just, oh, I do the shortcut and I'm good. Does that make sense? Okay. So the pink sheet, this sharp corner, is why piecewise functions are such a pain in the butt when we find a derivative. That's why we can't just find the derivative and call it good. That's why we have to be so careful with piecewise functions, is because just because it's continuous does not mean that the left-hand slope and the right-hand slope are going to agree with each other. That's why we have to go a step further, okay? So in our class notes, what we're going to do, if you guys remember, because this happened on that first test, right, where we had a piecewise function we were solving for a and b. Well, what if you have a piecewise function with an a and b in it, and now you're not just trying to find the piecewise function, you're trying to find the derivative of that same piecewise function with an a and b in it. So we're taking that idea, but we're making it a little bit harder, because we're not just saying make the piecewise function continuous. We're saying take that piecewise function, make it differentiable, okay? So make it connect, make the pieces connect, but make them connect in a smooth enough fashion that that slope at that single point where they connect is not a sharp corner. Don't let them connect at a sharp corner. Make them connect in a smooth way so that that slope actually exists. Does that make sense? That's what we're going to be doing today, okay? Or that's what the next set of notes is on. All right, so if you wanted to give this a title, we're going to say make the piecewise function differentiable. So we're not just checking to see if it is, we're going to make it differentiable by solving for a and b and forcing it to happen the way we want it to happen. So we're going to start off with a piecewise function, and we're going to have 3x squared plus 4x if x is less than or equal to 1, and 2x to the third plus bx plus c if x is greater than 1. And we're actually going to follow the same process that we followed in the video last night. So before you check if a piecewise function is differentiable, what do you have to make sure first? It has to be continuous, which means these two pieces have to equal each other when the one is plugged in. The two pieces have to touch each other. They have to connect. So we're going to check, and we're just going to make sure it's continuous first, okay? So I'm going to say it has to be continuous first. So I'm going to say 3 times 1 squared plus 4 times 1 equals 2 times 1 to the third plus b times 1 plus c. So before you even talk about being differentiable, you have to be continuous. You can't have a gap. And we know that because in the pink sheet, a discontinuity is one of the reasons you're not differentiable. So if there's a gap there, there's nothing you can do about it. It's just not going to be differentiable. So those two pieces have to meet together before we can do anything. Okay, let's clean this up and see what we're working with. So we've got 3 times 1 plus 4 times 1 gives us what? 7. Okay. We got 2 times 1 plus b plus c. Okay. So we've got 5 equals b plus c. That's about as far as we can take it. Okay. So now we're going to go on to the next step and we're going to find the derivative. So f prime of x. Now we're going to use our shortcuts. So what is the derivative of the first piece? 6x plus 4. What about the second piece? Okay, so this is if x is less than or equal to 1, if x is greater than 1. We need this to happen. We can't have any piece missing, so we need it to be equal to 1. We need it to be greater than 1. We want that stuff to happen, okay? So this isn't like before when we were taking absolute value graphs and we were rewriting them and we weren't sure if it should be filled in or not. It has to be filled in because it has to equal it, okay? Yeah, and I'm going to stick with the same one, the top one. The top one was where the equal to was, and so I'm going to stick with that. We can't, yeah, it was on the first one. Okay, so here I'm going to say the derivative being continuous means if I say left slope and right slope agree, does that make sense to you? Left slope and right slope agree, aka smooth curve. Okay. So you don't have to write this every time. I just want to make sure that we kind of understand conceptually what we're forcing to happen here when we do this, okay? So if the derivative is continuous, if we can make these two pieces connect to each other, then that means that they're having the same output, that from the left side, from this left side and this right side, that we're having the same y coordinate, and this y coordinate is a derivative, so it's a slope. So if the slope at 1 is the same number, that means not only do these two pieces connect, but that they have the same slope from each side where they do connect, which is very important for it being differentiable at that point, okay? Otherwise, we've got a quadratic and a cubic, and quadratics and cubics are both very smooth curves. So you can find derivatives all over those curves, and those are totally fine. So we're not worried about it otherwise. We're only worried about it at 1 to make sure we don't have that sharp corner, okay? So now I'm going to say 6 times 1 plus 4 equals 6 times 1 squared plus b, to make sure that my left slope and my right slope are equaling the same number, where those two pieces are connecting. All right, so what do I have on the left side? What do I have on the right side? And what does b equal? B equals 4. Okay, and so C equals, so -4, so equals 1. Okay. And so in conclusion, that means that f of x was 3x squared plus 4x if x is less than or equal to 1, and then 2x to the third plus 4x plus 1 if x is greater than 1. So that's the piecewise function that we actually had. And if we were to go back and graph those, do you guys remember how I taught you to plug these into your calculator? Okay, so let's try graphing this one. So if we did 3x squared plus 4x, x is less than or equal to 1. So what should I see where these two graphs come together? Should they come together? Should there be a jump? What should it look like? What should I see? They should come together, and what should it look like when they do? Smooth transition. So my graph had a little bit of a hard time graphing those. Maybe if we do it on Desmos, we'll see something look a little bit better. Let me graph this on Desmos real quick. Okay, people at home, graph that on Desmos. You will not be disappointed. It is very smooth. Whew, we just had a great math moment. That's wonderful. Okay, that's so smooth. Ha! Okay, next problem. That was example 1. Example 1. You guys did not get as excited as I did about that, but that was like very satisfying to look at. You guys do not feel satisfied by that? That was like a perfect transition. You guys, that was like two different functions that like came together. They could not have come together any better than they did. Did you guys not see that? I was like, choo. Like they, like two different functions. You guys, there's not some sort of incredibility about that? It's like, no? Okay, I feel like now is the time that I should confess to you guys that I earned the award in high school of most joy in mathematic discovery. So I did, and I accepted that award in front of the entire school. So that tells you something about how cool I was. Okay, all right. Oh, I should have included instructions for this. The instructions that would have been here. Go ahead and add these. The instructions that would have been here would have said find B and C so that f of x is differentiable for all real numbers. That's the type of instructions you might see for a problem like this. Find B and C so that f of x is differentiable for all real numbers. So before we even got started, since it was a parabola and a cubic, it was already differentiable for everything less than 1 and everything greater than 1. The only issue was 1, which is pretty typical with piecewise functions for us to only be worried about where it switches. Okay. Did you have enough time to write that little part? All right, let's do example 2. Example 2 says find A and B so that f of x is differentiable on negative infinity, infinity. I'm already excited to graph this one. I just know. I didn't graph these the last times I've taught it. And I was like, I should graph this so they can see it. And that was real nice, guys. That was real nice. I really wonder if the color calculators like make it look better. I'm gonna try a color calculator next time. I got one in my bag. You can plug it in the color calculator the same way I do it. There is an easier way, but the way that I do it still works on the color calculators. Yeah. All right. So what do we do first? Yeah. Make sure the actual function is continuous to start with. So we're gonna do a times 2 squared plus 10 equals 2 squared minus 6 times 2 plus b. So what do we have to start with this? Equals. So 4 minus 12, negative 8, plus b. Okay. And then we're going to get our derivative. What's our derivative? We can. We could do 4a plus 18 equals b. I figured I'd leave it since we had two variables anyway. We were gonna have to mess with it later. There's like no really good option. So okay, so derivative, we got 2ax. The 10 is gonna disappear when you take the derivative. X is less than 2. And then what about this part? Okay, x is greater than or equal to 2. Okay, and then what should we do? Okay, so 2a times 2. 2 times 2 minus 6. For a equals -2, right? 4 minus 6 is -2. And so a equals -1/2. Well, this is convenient. 4a equals -2, so we got -2 plus 18 is b. And so b equals, I'm already getting excited to plug this in. Okay, so we got -1/2 x squared plus 10. And we got x squared minus 6x plus 16. Okay, we're going to see if the color calculators are higher tech enough to show them actually connecting. I'm only plugging these in backwards because I didn't realize it was on the second line when I started. There's no rhyme or reason to it otherwise. Are equal to 2. Ah, very close. It still looks like there's a little gap in there. Ooh, that's so nice. Isn't that so nice? Oh, how beautiful. I love it. Everybody else love it? We should do like an art project where we connect piecewise functions smoothly to make a picture. You remember like back when like the Math 2 teachers would like make you use Desmos, so you have to like make a picture from like different shapes on Desmos? We should do that, but make it so they have to connect smoothly. You're like, this is the worst project I've ever heard of. Absolutely not. Other schools do stuff like that, and I'm like, What a dumb project. I don't want to. But now I'm like, this is so pretty. Let's do it. Oh, fine. You guys feel okay about this? It makes sense. We understand why it's a two-step process and it has to be. Yeah. Okay. So the practice work is the ones that are like the notes last night are so boring because it literally is super repetitive. So the ones last night are repetitive. And then the ones like this are a little bit more interesting because you're solving for A and B. But the ones that are like the notes last night are like, it's continuous, it's differentiable, it's continuous, it's not differentiable, it's continuous, it's differentiable, it's continuous, it's not differentiable. Like there's like no good way to do it, but we have to practice it because we have to be aware that sometimes it doesn't work. So, and then the ones that are like this are like, yeah, like this.